Well, looks like we can start. Welcome back, everyone. I appreciate you all making it in today, even if it's a small class just over Zoom. We'll do the best we can today. We're currently on week 12 of 16, so once this week is concluded, that's the 75% mark. And for our goal today, we're nearly done with section 7.2. We'll be spending some time next in 7.3, dealing with issues of prime numbers themselves more directly. Any questions at all, folks, before we get started with today's work? Okay, well, as the other announcement here kind of indicates, we're collecting a good number of algorithms so far. In the course, we've done several algorithms, but the algorithms in chapter 7 are really starting to stack against each other, layer on top. And this is the first one that we took a look into, mod and div. So just for another quick look into that one, here's the mod and div algorithm pulled up. It gives us the modulus of two numbers, n and k, and it also gives us the floor of two numbers. So if we run this, let's take out, say, mod and div for, how about we put in nk, we're doing n mod k. So let's do something like 35. That should be a really good test on this. So we know that 30 mod 5 should be 0, and that the floor, 30 divided by 5, should be 6. So testing this out, that gave us the right modulus, and it gave us the right floor. It is honestly kind of annoying that the function packs together two results, very important results like this. So if we want to extract one or the other, we're going to be revisiting this kind of syntax as well. Put in bracket 1, and we're referring to the first output for mod and div, and we get the modulus 0. Index into mod and div that returns a vector with two components by putting a bracket to say specifically we want the second component. And also notice annoyingly that R does like to index starting at 1, not at 0, but provide an index 2, and we get the floor of 30 divided by 5. So that would be 6 exactly, so is the floor. So that's our mod and div algorithm. We're going to be developing several others like we mentioned. All of them are going to just end up on this folder, and I'm going to be moving it down as we move down across the sections. I'm, as we've mentioned, executing all the pseudocode we write using this RStudio. If you have any questions about downloading or installing this, don't hesitate to ask. But if we're using something else, maybe Python, C++, that's just as fine. So here's where we left off. We developed the modulus and div algorithm, and now we're getting into issues about greatest common divisor, the GCD. The book also introduced least common multiple, but doesn't do too much with it, so I felt like we might as well throw it in here with the definitions as well, just for the sake of parallelism with the textbook. And example 8 is not something that really makes it to exams or anything like that. It's not really a homework problem, really just a warm-up question. We don't want to compute these things by hand, but if we're computing a greatest common divisor and a least common multiple, we might as well do it once by hand, just again for the sake of a warm-up. So here's the formal definitions of greatest common divisor, least common multiple. Notice that it's stated in a pretty interesting way. The greatest common divisor of two positive integers, n and m, denote greatest common divisor mm, is the largest d in the set of integers greater than or equal to 1, think of e as now the divisor, such that d divides into n evenly, and d divides into m evenly. So that really makes sense for a definition there. Let's now go ahead and compute greatest common divisor 30 and 15. If you see it already just by eyeballing this, then don't hesitate to throw it out. If I'm doing this by hand, this is how I probably actually start. Good old factor tree. Might have been a while since you've done these, but they're still useful here and there. The divisors of 30 include 2 going in 15, includes 3 going in 5, and that's all the prime divisors. That was so fun, we just do it all over again for 105. 3 is a divisor, but it's easier to divide by 5 first, so let's do that. 5 goes in there 21 times. Next divisor is 3, going in 7 times. And now we have another product of primes. So it doesn't really say it in this definition, But if I want the largest divisor that divides both, really I want prime numbers. And so that's kind of an indication of what the next section is all about. Prime numbers have an incredibly important role to number theory. So now that we have the primes out, we can relist these numbers. 30 is 2 by 3 by 5. 105 is 3 times 5 times 7. And there's other theorems in the next section that tells us this trick will always work because any integer that we pick can always be factored uniquely, aside from the order of the factors, into a product of primes. So there's only one way to build this table. Now we can say the greatest common divisor between the two integers. Well, it can't include a factor of 2 because it's not common to either. It has to include a factor 3, a factor 5, exclude the factor 7, and we have 15 altogether. So again, kind of a weird problem, really just a warm-up since we're looking into more of an algorithm for doing this more nicely and neatly without having to break out a factor tree each and every time. But now that we've done it, any questions at all, folks, getting to that line? Okay, so for greatest common divisor, we found the largest divisor that divides both of the provided integers, 30 and 105, 30 being n, 105 being m. Now, if we want the least common multiple, we're looking for the smallest divisor such that it's now backwards. Look at the role of how d is being played in the line above and now below. We want both 30 and 105 to divide evenly into a common divisor d, or excuse me, a common value d, and it's got to be the smallest one plausible. Once we have the list down below, we can just say least common multiple is, well, we can grab 2 now, grab 3 just once, grab 5, and also grab 7. I need to grab every single one of these prime factors because I need 30 and 105 to divide evenly into this number. But once we have all those prime numbers, it does the job. We're just really simplifying this down a little bit further. Let's see, that's 6 times 5 for 30 times 7 for 210. So my claim is 210 is the smallest number that both 105 and 30 evenly divide into. That looks totally plausible. But that's our warm-up to start the class. Any questions at all, folks, on doing either of those computations? Okay. Again, this might be some really weird nostalgic work that you haven't looked into in maybe 10, 15, 20, depending on how long it's been, even longer number of years. But here's another way to do all this. Here's the so-called Euclidean algorithm that was promised last class on Thursday. We didn't quite make to this spot. That's okay. It's good to do this kind of problem a little bit more fresh. What we're going to do with this is analyze this pseudocode, try to see if we can see what's going on with this. It's trying to return Euclid n mod n, but Euclid n mod n in this process is giving us the greatest common divisor. So let's see if we can track this for 36, 132. This is in red because I had, I believe, 35, 132. The greatest common divisor was 1, which meant in this recursively defined function, it had a lot of recursive calls, just too many steps. So to make this one a little bit more bearable, I upped the integer by 1 to make this a nicer problem. So here's the whole method, Euclid nm. We want positive integers. And curiously, the way this is written out, m has to be larger than n. So if we go to write out our own pseudocode for this to implement it in our studio, we might do a little bit of error checking, so it won't matter if you forgot to put the smallest one first. It's going to output the greatest common divisor of n and m, and it does it in a rather slick way, just a bunch of modular arithmetic. So let's trace the execution, Euclid n m, for these values here. So step one, we have a call to Euclid 36, 132. So first thing that's going to happen after we call this is we go to line 1 and the if block and do m mod n. So let's just run that part first, the modulus part. M mod n. This is not a bad idea to write down each and every time, because notice Euclid is giving the nm as the arguments we pass into the function. But down here, we're doing m mod n, so there's a lot of switching going on that is kind of harmful to our head if we're not paying attention to that, making the trace of this really small list of syntax a little bit more troublesome than it might seem at first. So m mod n is regarding 132 as m, 36 as n, so we're really doing 132 mod 36. So that's going to be our first thing. If it comes out as 0, then we just return what n was, 36, and our job is done. In other words, the greatest common divisor would be 36 if 36 does in fact divide 132 is the thought there. So let's do the modulus part in a really rapid way because we've already worked hard in implementing this. We might as well take advantage of this function. So calling, once I figure out where I am there, here we go. Calling n mod n div for 136, rather 132, 36. We get an output of 24.3. Recall that's a bit annoying. The first one is the modulus, so we really want just the mod indexed by going bracket 1, close the bracket, and that's the modulus. So 24. So we're done with the modulus part. Coming back up here, it said if n mod n equals 0, then our job is done, we return n. But this is not 0, which tells us the if block does not execute. It's the else block that executes on step 1. Else block, I'll just say runs. That's a little bit faster than writing out execute. So that's our first pass through this function. When the else block runs, we're doing a recursive call to the same exact function being defined in this way. So here's the run to. We have to do return Euclid. It's going to be m mod n. Let's track that carefully. This m mod n, we got it from here. So it came out as a 24. So m mod n is just 24 right here. Once we call the Euclid function recursively, the n value is not 36 any longer, or hang on. Yes, it is. I forget which one updates. The n value is still a 36, so 36 drops in. The thing that is nice about this is the numbers keep dropping in size every single time we make a recursive function call back into Euclid. So we know this is going to terminate probably rather quickly because of a quick edit from 35 to 36. So that was our first full run. We're really essentially starting back at the top and rerunning it all over again. Any questions at all, folks, with the getting down to step 2 before we finalize this one? Oh, there should be a 0 here. If that's your question, let me put that in. I was looking into n mod n equals 0, should have said not equals to 0. Okay, let's see what happens with this one. So we're making another call to Euclid 2436. So back up the top, we look into the modulus condition. We're doing m mod n. But we're using these values for our new n and m. So this is going to become 36 mod 24 next. That does not look like a 0, so let's get the value out. Back into RStudio with the mod and div algorithm. Let's call mod and div for 3624. We get a 12 out on that one, and 12 does have 24 mod 12 equals 0, so it looks like we're nearly done with this. First, we put in 12, not equal to 0. So that tells us, once again, the else block has to run. If doesn't execute on this one. So else block runs, which means if that block runs, yet again, another function call to Euclid and mod n. So we need to return Euclid. Are we going to put in m mod n? That part is just 12 going in next. The new n value, we look to this line, is found right here. So throw in 36. And we'll just see what happens. We need to do the modulus to see if the if block will run. So for the next line, we're right here by the red dot doing m, that's a comma down there, mod n, which is going to be, let's see, m is 36. Mod 12 on this one, and I think I forgot an n down there. So here's m mod n, and remember these are backwards. Really hurts my head when we go from here, switching them constantly. That's what makes this a little bit tricky in my opinion, just that switching. So 36 mod 12, that's 0, it goes in 3 times evenly. But that 0 is fantastic. This tells us we're matching up right here. We can now return in to the whole function. We're done making function calls to Euclid. We're just passing the result at this stage. So we have to say, well, if we're returning in, right there, what is in? This final return is going to be, let's see here, that n value here for the 12 when we did Euclid 1236. So this time we can say the if block runs and returns n, which means we return 12. So if we get 12 out, our foregone conclusion then is that the output is stated to be the greatest common divisor of n and m. So let's write down our conclusion. Down below, all we have to now say is, therefore, greatest common divisor by the syntax we just ran of the original integers 36, 132 is 12. That's our claim, at least. Well, any questions at all, folks? Looking at this syntax for the Euclidean algorithm? Okay, now that we have this algorithm right here, one thing we want to do is, let's see if it really works out as intended. We got a 12 out on this, but if we take this pseudocode, implement it into a programming language of your choice, I'll be using RStudio as usual, we'll be able to test it out on, say, something like this right here, and see if we really get greatest common divisor 15. So we're not going to prove that the algorithm runs correctly and definitely gives out the greatest common divisor n and m. That's part of the reading as well. Our author likes to also give a theorem along these lines to say this is a correct algorithm. So our job next is, let's just implement it and see if we can run it using some actual silicone instead of doing it this way, paper and pencil. So let's take all of this right here and now write it in to RStudio itself. This is the pseudocode, so we don't have to write fresh pseudocode unless we want to build it up a little bit more. But as it's presented, this would do just fine. Let me take off some of these marks here so we can really focus on it better. We'll call this one just simply Euclid NM, and we get this one all typed up. I'll get another version of it saved under the chapter 7 algorithms right here. So it'll be just another one of these files that you can much more easily copy and paste, modify as needed, that kind of stuff. So if you're not using RStudio, think of this still as pseudocode for maybe C++ or some other language. Okay, so back onto this one. Let's say we're defining a new function. I'm going to name it Euclid. Once I spell it right, Euclid, I'm going to store into the result a structure called function. We need to take in two inputs this time, n and m. I guess this is our second time doing a two-argument function. And first thing we might want to control here is a little bit of error correction. We haven't even worried about this at all for some of our other problems. For example, for n mod and div function, if we were to put in something like, say, 36.5, well, it worked out. I wasn't expecting that. How about 24.8? Weird. I'm kind of floored by actually taking digits. I was expecting a Stack Overflow. But to prevent any kind of weird errors on this one, let's actually control to force m bigger than n. So that way, if you gave something like 1,002, we want this syntax to still run. Let's think about that. We can put in an if condition. If we require m greater than or equal to n, let's think of these terms. The negation of n bigger than or equal to n is going to be n, let's write it this way, m, less n. So that's going to be the condition. We'll put in an if structure. If we passed in numbers that were in a weird order, larger than smaller, this condition is going to be triggered. So we can type in if m less n. There'll be no else to this one. We just want to swap things around. So we're swapping m and n's, essentially. Any volunteers for how to get started with this variable swap like that? This is one of those things where it's actually kind of tricky to come up with. One thing that you might try is m gets n gets m. That's definitely not going to work, not even close. Because the moment we do this, well, we just have m and n essentially, and then the next line is just going to reduplicate the same exact values for both m and n. So if this doesn't work, yet we want to force m less n, we still have some strategies here, because in this structure, only triggered when n is the maximum, we can just put in a temporary variable. We could call it t temporary. You might call it max, which is a bit worrying because that's a function within R itself, so maybe not the best value to use. Let's go with maybe t for temporary. T will get the result of the larger integer, which is n. So we're temporarily storing the maximum. Now, following this to the letter, we want m, that one, to be the maximum, and n to be the minimum. So we might say, well, we have a temporary for the max. Let's set n to m, the smaller value. Now m could be set to the max value t using that temporary variable, and that should do the job for us. So now we'll have the positive integers condition right here, m greater than or equal to m, automatically satisfied even if a mistake was made. That's an easy mistake for me to make, so good one to clear out right away. I'm not as worried about passing to things that should be integers and accidentally giving irrational numbers, stuff like that. But that's a good one to get out of the way. Next, we're on lines 1, 2, 3, and 4. But any questions so far with this structure here? Okay, let's clear this out and add the next bit. So just a quick if-else statement. So first condition, if m mod n equals 0. Now we can totally call the modulus function within any good computer programming language. If it's not standard feature set inside this language, that would be really, really weird. But you know what's kind of fun is all these definitions are starting to legitimately stack on top of each other. We already have a way to do modular arithmetic right here, mod and div. If we just make sure to call mod and div bracket 1, we're getting the modulus part and not the floor. But there's going to be other functions where we want just the floor for mod and div. So back over here, let's say if, instead of mod m mod n, let's call mod and div mn. If n mod n is identically equal to 0, so double equals to do this comparison check right here. So we're not trying to say the system should store anything. So if this comes out as 0, we do really fast process, return n. Then our job is done there. If it's not 0 right here, we need to go to the else structure. So else. Not sure if we really need curly braces for these short statements, but let's put them in anyways. Else return. Now we're doing the recursive function call. That's kind of the value of doing this trace problem first, to really see what's going on with the pseudocode, so that when we're about to implement, we have a better idea in our minds what's actually going on in each step. So when we go to this statement, we're passing to it the m mod n that wasn't 0 into the first position for the Euclid function. So Euclid, first argument is going to be mod and div m and n. And let me double check my parentheses here. 1, 2, 3 open, 1, 2, 3 close. Okay, we're still good on the delimiters. Last value is going to be n. And looking into the structure, I think we have it. Looks like all the curly braces are well matched to where they should be. These little arrows here in a good IDE system should be pretty helpful as well. But any last questions, folks, with inserting this?
Professor, I'm not extremely proficient in R, but I just wanted to make sure I understood. So you don't need that, what is it, the straight bracket 1, closed straight bracket after mod and div, because you need both of those numbers from
Yeah,
the function?
yeah, I needed to do the mod and div bracket
Oh,
1, like you mentioned. So that was my mistake on there. If I try to run this as is, there's no way it's going to work as intended. Thanks for mentioning that. In fact, let's run it wrong just to see what in the world it does, and then we'll put in the fix that you mentioned. Should have said bracket 1, exactly as you said. Because I'm passing 2 outputs, comparing it to 0. It's going to struggle right there for sure. Again, thanks for mentioning that, Michael. Other questions at the moment? Okay, let's see if it even gets ran correctly and gets stored up here on the functions list. So back down here, I'll hit Control A, Control Enter. It accepted it, but that doesn't mean the function will work correctly. So let's try it. As Michael pointed out, definitely is going to be broken, but let's see just how broken this gets. Euclid, we're going to call 36,132. And exactly where Michael said there's going to be a problem is right here. Error in the if statement. The condition has length greater than 1. It should have been exactly 1 because we did a direct comparison on something with length 1 right here. So let's put in the fix. This should have been kind of the guide back here when we were calling mod and div, just as a reminder, bracket 1 gives the modulus. So over here, we'll bracket 1. And then again a second time over here, bracket 1. Run this a second time. it definitely ran. And let's see if we can get a 12 out again on our example down below. So let's do Euclid 36, 132. And we got it, folks. The output of 12 came out. Well, any questions at all, folks, on getting this part to run? Okay, let's do another test. Let's see if this block even works, because we passed the function information in the way that was originally intended. M being the larger value, we put it in the second input. So let's call Euclid 132, 36. And hey, that's nice, we get 12 again. Doesn't mean we've proven the algorithm correct, but the author has proven this one. So long as we adapted the pseudocode correctly into our language of choice, we should be all set. Let's try another thing. That was an edit. It was originally 35 and 132, but the recursion on that, I think, had like 5 or 6 levels. Let's run that and just see how bad it would have been. 35, 132. We get a 1. That means the greatest common divisor between 35 and 132 is a 1. And in the next section, we'll call these numbers relatively prime based on this condition. Well, we've got a bona fide nice algorithm. There's a little bit more that we want from this. We're going to, in fact, extend this one a little bit further, call it the extended Euclid algorithm. But as it sits right now, it's just fine the way it is. Any questions at all, folks, running through the last bit of 7.2? Okay, so the section 7.2, majorly all about divisibility, modular arithmetic. So we developed 2 interesting algorithms, one for mod and div, given us modulus, the floor, and our last algorithm was for greatest common divisor. Now we're turning over to topics that feel disconnected for just a little bit, but rapidly or very soon it's going to feel like about the same kind of stuff as before. Section 7.3 on primality is going to connect mod and div function, greatest common divisor function, eventually as we get through the notes. Here's how it starts out. This one was revised today. I think I made a change on one particular number, if I recall correctly. This was something like 63 and 94, but then just like the other problem, when I went to actually practice this one, I realized, wow, the recursion's too deep. No one's going to want to watch us go through that. It was a little bit of a chore. But for this one, the recursion doesn't go so deeply. And so we can get a better view of the Euclidean, extended Euclidean algorithm here. So that was the one revision. We're going to try to keep these revisions to a minimum. But here's our brand new section. Starts out with a reminder definition of what we mean by a prime number. A prime number, or a number greater than or equal to 2, is called prime if its only divisors happen to be 1 in itself. And a number not prime we call composite. Nice theorem here. Our author proved this one in our induction section. Oh, not this one. Let's go to this one. The prime factorization theorem. This one was proven by our author in our section on strong induction. It says if you pick any positive integer whatsoever, then we'll find a factorization involving k prime numbers so that the integer n is a product of all those prime numbers. Pi right here means multiply p1 times p2 times p3, kind of like a summation notation for adding p1, p2, p3. But that's a notation we haven't seen a lot in this class, so let me just expand that. We're saying down here, pick any integer whatsoever, like the 30 or 105 we were working with at the start of class. Then you can find a listing of prime numbers, and this listing is unique. Aside from order, you can reorder it and it still works. So that n is equal to a product as I goes from 1 to k, a pi, but this notation, oh, I must write summations a lot more. This notation, less common, is uppercase pi, and it just means multiply. So this would be p1 times p2 times all the way through to pk. So that's the prime number factorization theorem. And just to get a feel for what's going on with the primes, our author also introduces this function, primes n. The prime number theorem is going to tell us that primes n, if it denotes the number of primes less than or equal to the integer n, then as n gets larger and larger number, this primes n and n divided by the log of n gets closer and closer to 1. This is an astonishingly deep fact of mathematics, which uses things like complex analysis, calculus to get to these kind of results down here. So we're in a section on number theory, which seems weird, but number theory is one of those mathematical topics that seems to be interconnected with just about everything in mathematics. And so this is a proof that involves lots of complex analysis. Our author says he doesn't want to even look into that proof, but it's still a nice theorem to get a feel for what's going on with primes. And here's an immediate application to the prime number theorem. We can just do some really nice estimates. For example, this is a hard problem to compute. It could be done, but it could take a while. Yet if you want just a really fast estimate of the number of primes less than or equal to 1 million, this will do the job. It's going to be approximately equal to n divided by the natural log of n. It doesn't tell us anything about the speed of convergence. So when it says as n gets large, this gets closer and closer to 1, meaning the number of primes is approximately equal to that. It doesn't necessarily tell us if that's large to get to really close convergence. We'd have to know a lot more about this theorem. But still, if we're estimating through it, this is a pretty fast problem. How many prime numbers are less than or equal to 1 million? We can say by the prime number theorem, there are about, let's take 1 million. That's the numerator right here. Divide by the natural logarithm of 1 million. And that will give us a number. Let's just compute this out as a quick computation. So 1, 2, 3, 4, 5, 6. Just got to count those out carefully. Divide by natural log. 1, 2, 3, 4, 5, 6. And let me try this again. 1, 2, 3, 4, 5, 6. Divide by natural log. 1, 2, 3, 4, 5, 6. Weird. I thought that'd be an easy computation for this system to handle. Not too happy with this numerical result right here. Could not find function ln. That makes sense. So let me try this again. I actually knew that. In RStudio, log is log base e. So this is the natural logarithm. Oh, and it even kind of indicates this right here. Base is equal to exponential power 1, or just base e for short. There we go. Now we have finally a result. It tells us we should expect, a lot of different ways to write this result. If you give me the decimal answer rounded to 0.41, then you're just focusing on the fact that this is giving us an approximation. If you gave me the number, let's say 72,382 rounding to the nearest integer, then you're just immediately saying we expect that as an approximation. So there are about, let's put here, 72,382 primes in this range. Well, any questions at all, folks, with that first use of the prime number theorem? Okay, and just because it's weird to do one problem and move on, let's try it out again on part B, approximating the number of 8-digit prime numbers. or whatever digit number prime numbers you're looking into. 12-digit prime numbers, 30-digit prime numbers might be stretching the technology a bit, but we could resolve any question like that in this kind of way. If we're dealing with the 8-digit prime numbers, we have to exclude 2. That is a 1-digit prime number. So in other words, probably what we should do to start out is find the total number of 7-digit prime numbers. Then when we put in the 8-digit prime numbers into this process, we're looking at all the prime numbers less than or equal to the largest 8-digit prime number we can think of, but then just subtract the prior results to get the correct value. So we can organize by going like this. The approximate number of prime numbers less than, now we're really interested in 8-digit prime numbers. So I want to find all the prime numbers less than the largest 7-digit prime number right before we move into 8 digits. So that's going to be 1, 2, 3, 4, 5, 6, 7. There it is, the largest 7-digit number. So let's find all the prime numbers, or approximate the number of prime numbers, is better said, less than that number. So using the prime number theorem again, we can say is 9, 999, 999. Hang on, let me count out my nines. 1, 2, 3, 4, 5, 6, 7. 999. Divide by. So that's the numerator written in. Now we just divide by the natural log of that result. 999. There we go. And my value for that, let's see, what should this come out as? Okay, that should be the right number of digits on both. I'm getting, rounding to the nearest digit, 620,421. We don't know that it's exactly that figure, but using the best estimate we have, this right up here, that's going to be our best go at approximation. So here's the 7-digit number, or the largest 7-digit. So now to get the number of prime numbers that have exactly 8 digits, we can just rerun this with 8 nines altogether. Run that function up here, subtract this result, and we'll only have the approximation for 8-digit prime numbers. So here's the next run on this. Therefore, the approximate number of 8-digit primes is, let's start off with this kind of estimate right here. We'll go 8-digit primes. So let's take the largest 8-digit prime number, 99, 999, 999, divide by natural log. This just looks kind of crazy on paper when you actually start to write this down. 99999, 999, minus these ones, which are largest 7-digit number and below all the way down to 2 as an estimate in primes. So take out the 620 or 21. And back to the calculator on this one. Just have to make sure we get the right number of nines. So let's count them off. 8 divide by log, same number. Subtract that figure. And we get this quantity altogether, close to 5 million. 4808 260. Primes. Quite a lot. And you can redo this kind of problem at any level right here that you'd like, just out of curiosity. Grows pretty quickly, but it grows in a controlled rate and divide by natural log n. Well, a predictable rate is better said. But any last questions, folks, dealing with that prime number theorem so far? Okay, well, this is kind of like the warm-up example one, looking into primes, taking a look into the theorems. That's a pretty fun one to deal with. Next thing we're going to look into is actually computing prime numbers. I threw this theorem right here, just in case we would like to use it. Here's some more interesting facts about prime numbers. Our author also proved this one with strong induction, I believe. I believe that was original induction, in fact. I believe that was section 5.2. There are, in fact, infinitely many prime numbers. So that's a nice, interesting fact. And if you want to start looking for prime numbers, and maybe you want to develop a syntax to make that happen, you can put in part 2 that any composite number greater than 2 is divisible by some factor less than or equal to the square root of n. This can give us a little bit of an optimization, because once we get beyond square root of n, there's no more divisors for a composite number. That's another really weird mathematical fact that takes induction to prove. And so using some of these ideas, if we would like on part 2, we don't necessarily have to bring it into our syntax. But what we want to do is write down the pseudocode that describes the so-called sieve of Aristophanes. So this is Aristophanes' method himself for computing prime numbers many hundreds and hundreds of years ago. Here's how it goes. It says the sieve of Aristophanes returns a list of prime numbers up to a given integer n by creating a candidate of primes in this list, 239. 2 is the first prime in that list immediately. So then the thought is, any multiple of 2 is automatically composite, because a multiple 2 is divisible by 2, therefore not prime. So we can repeatedly strike out all entries that are multiples of the first prime, 2. Then we just look into the next prime, strike out all multiples to the right, and keep on working our way through until we've checked everything, or checked up to the square root of n. Your choice if you would want to implement that part. So that's the idea of computing a list of primes up to a specific integer n. We want to write pseudocode that will take even just 2, but maybe it'll take even 1,000, something like that. Not too big, because this computer is not going to be very efficient at running this kind of syntax. It's not the world's best way to compute prime numbers, but it's an interesting way. Any questions at all, folks, about the sieve of Aristophanes before we actually go to write it out? Okay, once we have some good functioning pseudocode on this, we'll run this sieve of Aristophanes by hand to find all primes less than or equal to 40, and that will give us a way to look into our pseudocode again, see if we can see any mistakes inside of it, or maybe just understand it a little bit better. Honestly, with example 2, it's kind of a hard judgment call if we should do part B first or part A first. I decided to go with part A, but if you have strong opinions on that, let me know. There's no harm in actually doing part B first. Any questions, folks, before we begin? Okay, let's go for the pseudocode first then. This is going to be a new function. You could call it just sieve if you'd like. Let's make it seem fancy. Let's call this sieve underscore of underscore Eratosthenes. I'm not completely sure that I'm pronouncing that right. I usually say Aristophanes, something like that. So we have a sieve of Aristophanes. We give to it just one input, one argument, n. So let's say C of Aristophanes is a function with n as input. Now we have to do some stuff to figure out what really is going on with this description here. And maybe a good idea to go with is, as we build out this pseudocode, let's run a particular example. Let's say n is 10. So we give it an integer, our example is 10. We're going to create a list of candidate primes, 2, 3, all the way up to n. So you could call this list underscore of underscore candidates, but that's getting kind of long to write in. I'll just call this list. Oh, well, it's a candidate primes, so let's be a little bit more descriptive. Let's call it P list. So prime candidates list, kind of shortened up from what's been said right here. I want a list that goes from 2 up to n. And one way to write this out is a structure like this, which is pretty common. 2:n builds a list really fast in many different languages. For example, if I go 2:10 over here, I get this list, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, we might as well just take advantage of that. Let's take this list. So for n is 10, that's the list we would build out. In our pseudocode, it would look just like this. So let's see what happens next. This is some really interesting syntax. The verbal description is short, and somehow this allows us to compute primes as an interesting method. Let's see what it does next. Well, after we build the list, it repeatedly marking the first unmarked number, p, as prime, striking out all entries of that are multiples of p. Let's pause right here. Every time we go to this structure, we automatically create a list indexed in this way, and the first entry of that list is automatically a prime number. So the first unmarked number is a prime. But we have to modify this list a lot as we go. I want to output only the prime numbers to this. So we're going to have to work really carefully on the indexing. Let's say I is an index. So here, this is I equals 1. Annoyingly, I'm using RStudio, the index is starting at 1, just as a reminder. So if you start at 0, sorry about that. This might be slightly painful. Don't hesitate to just write in 0 if you prefer. So next, I equals 3. I equals 4. I equals 5, 6, 7, 8, and up to 9. So always starting at 2, always starting at the first prime. What I need to do is filter out this list by striking out all entries in the list that are multiples of p. But the very first thing I should do is index into the very first prime. So I'm going to call this p index. We're going to use a while loop structure, and this is going to increment all the way through to the next prime as we go. But it starts at p index is 1. We're indexing into 1 to grab the first prime 2. And now we're on this part. So here we're doing the while loop structure. But before we get to that part, any questions so far to this stage? Okay, so let's say while p index is going to be incrementing 1 by 1 as we filter through the list right here, crossing out the multiples of the first prime. So we'll start by saying while p index is less than or equals to the size of this list. And it feels really natural to put an n right there. But we're crossing out values in this list, updating as we go, so the size of the list changes each time we iterate through a while loop. Because of that, we should probably use a new structure or a new function that goes along these lines. Just go length a P list that's gets shorter and shorter as we go, if n is something like in the range of 10, because we're crossing out composites. So we can't put an n here. We have to put in the new size of the list every single time we run through the while. So that's the condition that triggers the while loop. And now below we'll write in the structure. Let's see here. What should we do next? Striking out all entries in the list that are multiples of P. We never grabbed the first P, we've just indexed into it. So we should actually grab that 2 right there, the first prime. Let's write P is assigned P/list. And well, I can't give it P list entirely, that's too much stuff. Pretty much we're just doing like what we did over here. A bracket is going to subset into this, and we want to bracket into index 1. But we can't say index 1, we have to use P index. It's initialized to 1, so it runs correctly on the first run through while. So we'll say P index. So now at this stage, we have extracted a prime in P list, where P list is this right here for us, a list of all the prime candidates. Now we have to filter through this list. We have to remove stuff that's a multiple of 2. So the 4, the 6, the 8, and the 10 all have to be deleted. All of the evens except for 2. So we need a condition where we exclude that all at the same time. Essentially what we can do to make this as painless as possible, less loops and other weird stuff, is write out a whole new index into this. It's going to be a vector that tells us which ones of these do we grab, which ones do we just exclude. So let's call this new index. It's a temporary structure only inside the while loop. So let me make this a little bit bigger so it feels more indented. Okay, so next structure is going to be new list index. So we're going to get a new index altogether. It's going to be set into, here we're doing a logical structure like from chapter 3. So I'm going to connect this with an OR statement. And first thing I want to take a look into is, I don't want to delete this 2 right here. So we should probably say something along the lines of P list. When I say P list, I'm talking about the indexing right up here, or excuse me, no, it is these values down here. I want P list to be less than or equal to P. So if I do that, I'd be grabbing the 2 right here. Then next, we'll say or, might as well just draw in the logical structure that we use in that chapter. Here's where I'm going to do the method of, or the process of striking out all entries in the list that are multiples of P. Well, a multiple P would mean that the number mod P is 0. So I'm going to go through here. This is calling the P list again. I want to take everything in P list, do mod P against it. So this is a vector now, but I'm going to apply mod P to all entries inside that vector. And I want that to be not equal to 0. So that means we're only carrying into the new list index those things that were non-zero, meaning stuff like 5. 5 mod 2 is 1. We don't want to cross that one out. We want to cross out this one. This is a multiple 2, and 6 mod 2 is 0. So not equals allows all the primes to survive. This part right here allows us to include 2 as well. So we have a new index list. That means we have to update our listing up here, P list. So go the list of primes, P list, is reassigned itself. But this is going to give us now a way to index into just the ones that didn't get crossed out by these conditions up here. So I'll go new list index. So what we've done now is we took the prime. This part allowed us to keep that prime. This part is going to delete any multiples of those primes. And this part just updates plist. So once this runs through with 2, we're going to delete 4, 6, 8, 10. Our new list is just 2, 3, 5, 7, and 9. One composite still left in that list. That means this wouldn't be done. We have to update the index starting at 1, now to index 2. So 3 has to run through the while loop again. P is going to be set equal to 3 by this. But the way we increment turns out to be kind of nasty in a way. We have to be extremely careful. I can't just say P index plus 1 inside this loop right here, because we're constantly changing the list inside this loop. I don't know how big the list is after the deletions. So just to make sure our index doesn't exceed the size of the new list of candidate primes, we need a new if structure inside the while loop. So here's how this next part will go. Let's say if. Now what we're modifying this time is P index. And we don't want it to exceed the size of our list after the deletions. So let's write in if P list. And we have to increment it, right? So let's do that right here. This is where we might have incremented it willy-nilly, not worrying about the size of the list changing, but we're putting it inside here. If P list is less than or equal to the length of, oh, hang on, that's a mistake. Not P list plus 1. I'm not including extra things in the list. I should say P index. That's the thing that's going to be incrementing. Let's track this a little bit more carefully just to see the role on this. That can really help with that kind of error just made. P index was right here because I was grabbing the first prime out of P list. And where else does P index occur? Right here. That should have said P index. Let me try again with this. P index plus 1. Okay, that will save us there when we try to implement that pseudocode. So now, if P index plus 1 is less than or equal to the length of P list, that's another thing that seems to be getting easily conflated. Let's track this as well. So here's P list. Over here, we were making sure the index didn't exceed the size of that list, which size constantly changes on us. Over here, we were indexing to the list. And by the way, again, this is the list we're referring to. The index is above. Let's see, we did new list index. We're looking at the primes less than or equal to P. And we're doing modulus or mod P on every entry in that list. Over here, we updated the list with the new indexing. And now finally here, we want to say length less than or equal to the current length of P list. Okay, so if that part's true, then all we're going to do is go P index is reassigned as P index plus 1. So we finally did an increment. Kind of a weird way to be forced into incrementing on this one. But the sieve of Aristophanes is a weird algorithm, so not too surprising that the process is weird on incrementing P index. What are your questions, folks, so far to this stage? Okay, so this is a if structure. We can just, for the sake of making sure we leave the while loop at some point, also put an else. Let's just say break. So we'd be breaking out the entire while loop. I was really thinking I was going to get this in one page easily. So let's close that parenthesis. Now closing the parenthesis for the while loop on this line. And if we're done with the while loop, that means we have successfully filtered out all the composite numbers from this list entirely. So that means we can just return the prime list. Our job is done right at this stage. So the function ends by saying return p list. No longer a candidate list of primes if we did everything correctly and there's no misplaced comma when we try to actually implement this into a language, then we'll really have a list of primes. Any questions at all, folks, on this full write-up for the pseudocode on this one? Okay, next part is see if this actually runs. But I want to just give you a heads up on the homework assignment for 7.3. We're in a sense kind of looking into the problem. Let's see here. Problem 4. Problem 4 is going to ask you to do a variation of the Siva Aristophanes by not actually outputting the number of primes, but instead counting the exact number of primes. So you can write pseudocode that counts the number of primes less or equal to n. One hint on that is that means you're not going to return the list. You want to return the length of the list right here. Then run your pseudocode on problem 4 to count the number of primes less than or equal to 100,000. So we're going to reuse this problem as a homework assignment, slight variation. So let's see if we can get this implemented correctly. This is going to be kind of hard to fit everything in. I think we'll make it work. This is going to be our next algorithm. So we have 3 now. We'll call it, just as we did up here, sieve of Aristophanes. Definitely dispel that, but we'll just go with it. It's going to be a function accepting one argument, n, and lots of fighting inside this function. So first, you generate a list of size 2 through n. In R, instead of using equality, assignment to a variable is usually just a left arrow like that. So I'll go 2 colon n. Then we initialize our index to 1. We're automatically indexing into the very first prime. This is where I took a lot of time this morning just to make sure my logic was coming out correctly. The while loop needs some extra care. So while the index is less than the length of the list, less than or equals to, looks like a left arrow, but just put in your symbols back to back, the less than sign first. Length is a function. Give it the vector p list. And we have our while structure going. Here we grab the very first prime number. So p is go into the p list of primes, p list, use the bracket structure again to index and put in p index. So that's just saying inside here, our listing of prime candidates, p index is 1, so we're grabbing the first element, which is automatically prime 2. Here's the sketchy part next. We need the new list index, our temporary variable. The new indexing is going to be defined as this logical structure. So first, p list, less than or equals to p. I don't have a symbol that goes like that in R, but the symbol for OR is just the vertical bar. So hit Shift and the button above Enter to find that one. And we could use mod and div, but the tragic fact here, folks, is that our mod and div is not overloaded to accept a vector in the first component. That would make this a much longer function. However, there is a mod operator, like we mentioned in any language, essentially. It goes like this inside of R. Let me first rearrange this a little bit better. So we're going to go P list. We're passing a vector. For the modulus operator, it's double percentages for modulus. And a vector is accepted here. It's just going to do a pairwise modulus operation on mod P, the prime we just extracted, for every entry inside this vector. Next thing is we want to write in not equals to 0. And that's, always kind of interesting to see how this is implemented. Anyone happen to recall a way that that's usually implemented, the not equals to operator or comparison check?
In a lot of language, it's either exclamation point equals or tilde equals. I'm not sure what it is in R.
You're right on the money. It's the exclamation mark equals. So that one would do the job for R. And if you're in a different language, try out that other suggestion as well. Tilde equals probably is going to work in a lot of other things. So let's go exclamation equals 0. So saying the mod is not 0. That gives us the new indexing. So we just update the list right here. And suddenly that's jarring. Let me fix that part. So redefine the list. plist gets plist, pass the new list index that we just defined. We want to increment, but we have to do in a slightly painful way because the size of our list just changed on that line right there. So another check, if p index plus 1 is less or equals to the length of plist, we need to do something. Here's the incrementing. P index gets P index plus 1. But we also want to break out of our loop at some point. So let's put in the else part of this. So else, that's a nice statement. Break. So at this stage, we would be completely done with the while loop. Let me see if these match up the way we expect. It's pretty good. We want to return the list of all of our prime numbers. So down here, just say return p list. So this is the moment of truth. We're kind of close to the end here. If we completely wiped out all the composites on this, we should have also wiped out the 9. So we're expecting 2, 3, 5, 7 on this. Let's see how it does. Well, Control A and Control Enter stored the function. Here's the sieve of Aristophanes on our function list. Now let's see if we can pass to it 10 and get 2, 3, 5, 7. So C, Aristophanes at 10, and that did not work. Could not find function length. I think I misspelled the word length. Let me take a look into this. There's a G there, and G goes here. It's a bad time to be not great at spelling some days. Let's try this again. One error down, sieve of Aristophanes at 10 gives us 2, 3, 5, 7. Looks like it's actually running correctly. We can do the sieve of Aristophanes at 100, and here's all the prime numbers computed from 2 to 100. That looks legitimate. These are the prime numbers. Let's see how it can run up to 100,000. So here's a test. At 100,000, the red stop button here tells us it did take a while. And I reached the max print here, so we've omitted 8,592 entries. We're not showing all of those prime numbers, but here's a pretty good list of primes. We can also adjust the features here of RStudio if we really want to see those primes. Could have also stored it into a vector, have it print out into a PDF or a notepad file, anything along those lines. But in the end of the day, we have a new algorithm. It's nice to be able to now compute primes. And this is just another extension of our work in number theory. If we're going to work on prime numbers, we have to know how many there are, that's example 1, and how to compute some. Well, any last questions, folks? Running through that syntax there. Kind of exciting to see it works.
Professor, on the homework where it talks about executing it in a program, is there anything that you want to see on the homework to verify that we did that, or is it just kind of an exercise we do on our own?
It's kind of on your own, yeah. If
Okay,
you
thank
want
you.
to and you had the gumption for it, you could do stuff like this. Put out screenshots into your homework assignment. A few people have actually been doing that already on some assignments, but it's not a strict requirement. So if you just give me the results, that would be totally fine as well.
Thank you so much.
Yep, absolutely. Other questions at the moment? Okay, well, have a great night, folks. If you run into any issues getting this kind of code to work, don't hesitate to write to me. I'll be very happy to help out. I'm not great at coding in a whole lot of language. I do like 99% of my work in R, but I can still be very happy to help you out, getting it working on your end. But have a great night, folks. When we come back on Wednesday's class, we're going to move into some more interesting algorithms like the extended Euclid algorithm. This one is a little bit confusing, and we're going to get into interesting stuff like the Chinese remainder theorem as well, solving equations involving modulus. So getting deeper and deeper to number theory. Our goal is to get into some cryptography by the end of chapter 7. But have a great night, folks. I'll see you all next Wednesday.